So now let's use any method that applies to find the circulation on the unit circle for each of the following vector fields. So in part A, we have a radial vector field, where vector field f is equal to x comma y, and you can see it's radiating out from the origin. Okay, so the circulation for this would be equal to the double integral over the region of g sub x minus f sub y. So g sub x minus f sub y, that's the curl, dA. Okay, so just a reminder, this is called the curl of f. All right, so g sub x, well, this is f and this is g. So g sub x is actually 0. And then f sub y is also 0. So this is 0. As a matter of fact, we can tell that the curl is 0 right here because we saw that this became 0. And that means that our f was an irrotational vector field. It's a conservative vector field. Right? It has no rotation to it, which you can see when you look at it. Everything's coming out from the origin. It has no rotation. It's irrotational. And therefore, the circulation is 0. All right. Now, what about if it's a rotational vector field? Well, that's not going to be as easy. Okay, so the rotational vector field, let's see here. We have circulation is equal to the double integral of g sub x minus f sub y dA. All right, so this is the double integral. Let's see if it becomes 0 like it did on the last one. G sub x, so this is now f, and this is now g. G sub x is actually 1 minus f sub y is negative 1. So that's going to be 2. Okay, so just thinking about how we want to do a double integral over this region, right? Our region is the interior of this curve. So it's a circle, right? And we learned in the last chapter that circles, and I should say it's the interior of the circle for all of these, right? We learned in the last chapter that for circles, it's a lot easier to work in polar coordinates. So let's switch this from being 2 dy dx, or 2 dx dy, to 2 r dr d theta, because it would be easier to think about polar coordinates. Right? A circle makes it easier to use polar coordinates. All right, well, r is going from 0 to 1 because this is the unit circle, and theta is going from 0 to 2 pi. So we already know that we can take the 2 pi out, and then we can integrate this, which would be r squared. So it would be 2 pi r squared would be my integral from 0 to 1, and that would be 2 pi. There we have it. All right, what about the last one? Okay, so this is a vertical vector field, right? All the vectors are pointing up. Okay, so our circulation will be equal to the double integral over the region. G sub x would be 2x minus 0, because the integral, or the derivative of that is 0. Right? This is our f, this is our g. So dA. So that would be the double integral of 2x. Well, actually, let's think about this. It's a circle still, right? So it would be, again, wiser to do this with polar coordinates. Polar coordinates are easier to work with. Sorry, my one highlighter was dying there. Okay, so we're going to make this polar, again, because polar is easier. Now, in polar coordinates, x is r cosine theta. So that's 2x, right? This is that, right? And then we always, when we switch to polar, have to make it r dr d theta. Theta is going from 0 to 2 pi. R is going from 0 to 1, just as before. Now in this particular case, we cannot use our trick of just taking the 2 pi out because there's a cosine of theta in there. So we're going to actually integrate this. Now the integral of, now notice what we have here. We have 2r squared times cosine of theta, right, if we think about these pieces. So let's integrate r squared right now. That would be 2/3 r cubed, right? I can bring the 2/3 out in front. That's not hurting anything. So it would be r cubed. The r cubed is going from 0 to 1, and you're still multiplying by cosine of theta d theta. All right, so that would be 1 in there. So this is 2/3 integral from 0 to 2 pi of 1 cosine of theta d theta. The integral of cosine is sine. So this is 2/3 sine of theta, where it's going from 0 to 2 pi. And the sine of 2 pi is 0. So that's 2/3 times 0, take away 0, which is 0. And you can kind of see it as you look at it, right? So remember circulations, how much the vector field's pushing you along. And so it's pushing you this way a lot, but over here you're going completely against the current in the exact same amount that you were going with the current over here. So going with the current, it helps you, but going against the current, it hurts you. Going against the current, it still hurts you, and then it helps you. So it all cancels out, right? The positives and the negatives canceled. That's different from this particular one. In the first one, it's 0 because there's no arrows pointing with the curve, right? The vector field's completely running across the curve. We have no circulation. We actually have tons of flux, right? But no circulation. So this particular one, if we want to make a note, right? The circulation is 0 because the vector, right? No part or no vectors in the field, let's put it that way, in the field F are helping. Move along the curve, right? Right. So if you're thinking about the motion, none of the vectors are helping, not at all, right? Whereas in this one, tons of vectors are helping, right? So this is a positive number, so this has a positive circulation because look at the arrows, right? They're going right with the curve, right? The vector field of vectors are pushing along the curve. Whereas in C, it's pushing with you and then it's against you. So the circulation is positive over on the right and it's negative over on the left in the exact same amounts. So the circulation is positive on the right and negative on the left, so they cancel out. Because it's the same amount on the left as it is on the right. It's just positive over here and negative over here.